and thanks to so many of you for showing up today. These sessions hosted by myself and Dr. John Moreau. So today we have Dr. John Telling from Newcastle University joining us. And John started his science career as an undergrad geologist and then a master's in geochemistry. And thankfully, and finally, when he came to do his PhD, he had the very good sense to bring microorganisms into the fold, and he was looking at metal cycling in deep ocean sediments. John then went on to do his first postdoctoral job at the University of Toronto in Canada. And after this, the University of Bristol snapped him up and wisely clung on to him for 10 years. And during this time, he did some really fantastic pieces of work on glacial nutrient sources and cycling and their impact on microbial communities. And most notably for me was his work on glacial nitrogen cycling and also his work on the role of subglacial rock crushing in sustaining subglacial life. And actually, it was during this period that I first met John. He was out in Greenland, as was I, and he was braving it out in one of his many years at what's fondly termed Camp Doom, likely surviving on only mackerel and canned peas, as the legend goes. So in 2016, John moved to Newcastle University, first as a lecturer and now as a senior lecturer. And while he continues to have an interest in glacial environments, he's also now stretched across to extraterrestrial landscapes. And I believe he's part of the ExoMars mission, which looks at past and present life on Mars. So welcome to the session today, John, and thank you so much for giving up your time. We really appreciate it. If you, the audience, have any questions for John or discussion points for John or each other, then you're very welcome to raise these at the end of John's presentation. As always, I really welcome you to voice these yourself, but you can also use the chat function and I can try and ask them for you. As you'll hopefully have seen, this session is being recorded, so please just bear that in mind. So I'll hand over to you, John, and feel free to start just whenever you feel ready.
Great. Thanks, Karen. Thanks for the introduction. And actually, thanks for organising this as well. I think it's great to have the geomicrobiology seminars. So that's brilliant. Right then, so what I'm going to chat about is what lies beneath, so subglacial biogeochemistry. This is work that it's not just me who's done it by any means. The work I've done on subglacial settings, I first started with Gemma Wadden when I was at Bristol. Work she was leading there. And there's been a host of other people that I've worked on this over the years at different field camps, in the labs, different places. So this won't be an exhaustive list, but thank you to everybody who's helped out on subglacial research over the years. What I'm going to sort of top and tail this talk with is this. So in 2014, there was a new subglacial lake discovered in Antarctica, the western part of Antarctica. This shows its rough location on the little map there. So this was found by a Chilean institute, the Centro de Estudios Científicos, and the lake CECs is named after that institute. So the nice thing about this lake is that it's in a different area to the previously explored lakes. Okay, it's a potentially more isolated area, potentially a deeper lake. Sediments probably be isolated from the surface for far longer. So exploring this lake should give us really good insight into what's happening beneath the ice sheet. So there was a call out earlier this year to get some funding to help with the science exploration of this lake. So it's a kind of Chile-UK consortium. So I'll put in as part of a bid with, again, Bristol and Southampton, which has been provisionally funded. It's called Atlantis. And what it's really about is to try and figure out the ecosystem dynamics of this lake. So what's going on there? What's controlling the ecosystem, energizing the ecosystem, limiting it? What's it doing to nutrient cycling within the lake? Now, this is currently on hold. It's been delayed due to COVID, so hopefully it will still go ahead. Provisionally, pre-seasons destined for 2021-2022 with the drilling in the austral summer of 2022-23. But that's, as I say, still on hold. But it's what I'm going to use to kind of focus the end of the talk on. So I'm going to kind of, up to then, give a kind of introduction to subglacial environments, provide the setting, and then I'm going to give what is probably a very biased view of subglacial environments. It's my own sort of journey. So as Karen was saying, I wasn't originally a glaciologist. I was a geologist, a geochemist. I hadn't even seen a glacier. So I did this postdoc in Canada on something completely different, PhD on something completely different. And then I saw a job advertised at the Bristol Glaciology Centre, working with Gemma Wadham, to set up a new low temperature experimental lab there. So I went for that position as a technician and got the job. But as part of that, because I've done a fair bit of fieldwork before, I was also thrown into helping out on various field trips. And that's kind of where my glaciology journey starts, with, you know, almost immediately after starting at Bristol, getting involved with helping out and going on all these trips, different glaciers, and trying to sample the subglacial environment. It's called Microbiology with a Chainsaw, topic 1 there. Then I'm going to briefly talk about studies after that, again, involved heavily with Bristol, where we're looking at catchment scale carbon and nutrient fluxes. So rather than going to different places and doing sort of spot sampling, it's basically sitting there, one spot, really good spot in Greenland, and trying to get a sense of the kind of catchment scale of this glacier, so the kind of the whole glacier scale. And then from there into research I'm doing at the moment onto crushing stuff with a hammer, ball mills, it's known as mechanochemistry. So what happens when you crush stuff, right? What kind of novel chemistry can you catalyze that might influence the microbial communities that live under the ice? But obviously glaciers are really effective crushing machines as well, or they can be. And then finally, say I'm going to end with trying to bring a few things together and talk about how things what we might find in this newly discovered lake, I guess, and how it might differ and be the same to what's been found before. So to give you a little background, okay, glaciers and ice sheets you probably know this, cover about 10% of the Earth's land masses. They account for about 70% of the Earth's surface freshwater. That's now, in the past, during glaciations, this was much larger. It would have increased to about 30% during the last glacial maximum. There have been periods in the Earth's past as well, the so-called snowball Earth events in the Proterozoic, where that coverage might have gone up to close to 100%. So there's a lot of ice. There has been a lot of ice. So I guess when most people think about that ice and you see in the news, it's probably to do with, at the moment, global warming. So it's about, okay, so how the melting of glaciers, melting of ice sheets might affect sea level rise to do with climate change. But there is another angle to them as well, which is the habitats that they can host, particularly under the ice, the ones I'm interested in at the moment. So when you look at, say, that picture, you might think it's a very inhospitable environment for anything to live, an unlikely place. And even when you look at the sediment coming out, there's no real visible sign that it might be alive under there. Right? You need a microscope to see what's down there. But actually, when you look into what is there, they are habitats. They're important habitats on Earth. They're very large habitats on Earth, and they could have regional, even global implications for elemental cycling. A key first question when you get into subglacial habitats is what supports that habitat. It's the water. So where does the water come from to support life under ice? And the answer to that will be different on which particular glacier, which sector of the ice sheet that you're looking at. So this shows a little image, a nice one I found in a paper by Andy Mitchell and Giles Brown, of a typical alpine glacier. So here they're saying that a lot of the water is coming from surface melt. So you got kind of one of the most obvious things you might think of, yeah? So you got the sun creating heat, melting the snow, melting the ice, okay, it's starting to run off. And we have cracks or fissures in the glacier, crevasses and moulins. Some of those can go down to the base of the glacier, and that is one important source of water to some glaciers and some parts of ice sheets, but not all, yeah? But that is an important one for many. So that's where you get surface runoff, snow, ice, maybe even a bit of direct precipitation that can flow down these to the base of the glacier or the center of the ice sheet. But you do have other sources of melt as well. So the second one on that list there, englacial melt, that's strain, yeah? So actually within the ice mass itself, these glaciers are moving, and the strain within that ice mass can actually itself create some liquid water, depending on the conditions and the pressures. Third one there, basal melt can be very important. So this is where you can have underlying geothermal heat under the glacier. Yeah, so heat coming up from the earth can start melting the ice. You can also have basal friction. So as that ice mass is moving across the sediment or rock, then you get friction, and that itself can create the heat to melt the ice. The thickness of the ice can be very important, particularly you'll see when you get up to ice sheet scale, to do with pressure. So with added pressure, but the height of the ice, it can reduce the melting point of water itself. So you can get water under the ice sheet at the thickest part of Antarctica, for example. I think the water's about minus 2.3, minus 2.4 degrees before it reaches its freezing point. And the pressure itself can also help create more energy. So more energy for grind. If you've got a greater mass of ice, it's got more potential energy there to convert into kinetic energy to do the grinding. The pressure itself can be on big scales like ice sheet, also small scale. So if you have little irregularities in your bed, you can have ice moving over these rocks and you'll get an increase in pressure at that rock, which can, even in a cold glacier, get a little bit of melting. Then it moves past that little rock, it will start to freeze again. It's a process known as regulation. So you can get these effects at different scales. And also, I guess, what's in the water can be important for when it freezes. So if you get enough weathering going on over long enough periods of time, enough sort of salts can get in that water to act as a sort of antifreeze and lower the melting point too. And an important thing about glaciers and ice sheets is that they're not static. They don't stay the same. So over a season, for example, then you'll get snow forming, you'll get snow melting, you get the hydrology of these things changing. So for a typical alpine glacier like this one, you might start off at the beginning of the melt season before everything starts melting with a very kind of low flow, what's called distributed system under the glacier. Okay, so it's sort of out of contact with the atmosphere, slowly moving through these little interconnected channels. Then as the melt gets going, stuff starts pouring down the moulins, the crevasses, down to the base. That's when you get more open channels forming, much faster flow of water, get much more oxygen in the water there too. And you get sort of similar aspects with even ice sheets, where you might think they're completely isolated from the surface, but even sort of subtle movements of ice on the surface can affect the stability of lakes underneath. You get the subglacial lakes draining and refilling at regular periods. So they're very dynamic systems. Not all glaciers are the same. Okay, some are cold, known as cold glaciers. Some are hot, known as temperate glaciers. When I say hot, that means that they're kind of melting point. Yeah, so they're at the melting point all the way through. And some are in between. They have like temperate and cold areas. Yeah. And again, these can change. So for example, with climate change, if you get a glacier melting away, what was once maybe a polythermal glacier may eventually become completely cold-based. So again, dynamic systems. When we look at an ice sheet scale, well, some of you might be surprised to know that it's really the sheer thickness of the ice that causes it. So about 60% of the base of the Antarctic ice sheet is at the melting point. The reason for that is because of the thickness of the ice, it almost acts as an insulator, and then you have geothermal heat coming up from underneath, and this causes the ice to be at the melting point. So the estimated total volume of water under the ice sheet, and this is a kind of schematic image showing what it would look like if you lifted all that ice up, is about 4,000 to 12,000 kilometers cubed of water. So that's a large amount of fresh water. And they've been described as sort of the largest wetlands on Earth, and we still know very little about them overall. I think in total, there's been about just over 400 subglacial lakes, which have been defined by geophysical techniques above the ice to be residing below the ice. And a lot of those may be interconnected, at least at some points, by interconnected rivers. On Greenland, there's a recent survey as well. So we've known for a while there's certainly melt around the outside of the ice sheet, but there's now also known to be numerous subglacial lakes, often on a smaller scale than those in Antarctica. But this diagram on the right is showing the known distribution at the moment of subglacial lakes under the Greenland ice sheet as well. So what about subglacial environments as habitats? So it was actually relatively recently when people first discovered life under the ice. So it was in 1999, a paper by Martin Sharp et al. In geology. They first described microorganisms in subglacial environments from some alpine glaciers. Then in 2000, next year, then Mark Skidmore and others, they actually measured activity within them. They used different radio traces to actually show that these things weren't just there, they were active, even at these low temperatures. And it was only as recent as 2013 that the first subglacial lake in Antarctica was actually sterilely drilled into by a US team. That paper there, Christian and all, 2014. And this was the first one to really kind of cleanly sample subglacial environments in Antarctica. So why should we care about looking at these environments? So I guess from what I've done from my own research, I've been associated particularly with these first two, and maybe now getting into the third one there. So in terms of carbon storage and release, if you think about what happens during glacial cycles, you get glaciers which are advancing, okay, during glaciation. When they advance, they can go over pretty much large amounts of both marine and terrestrial organic carbon, okay? So what happens to that carbon? Is it slowly recycled under the ice over glaciations, maybe recycled to methane, and then maybe that can be emitted in a short pulse, perhaps, as things start to retreat, or does it just stay there and nothing happens to it? Yeah, so that's one question I'm going to start off by discussing. A second one, if you look at this picture, this is of a glacier known as Leverett Glacier in Greenland, southwest Greenland. You can see on the left-hand part of this image, this portal, this hole into the ice. That's where all the water's coming out, and it's really turbid. Yeah, you can see this turbid water. And that's really full of nutrients, particularly rock ground nutrient, things like iron and phosphorus and silica. And the sheer amount of these nutrients that can be crushed up and emitted out into the ocean, that could be important for helping to support marine life, phytoplankton in the oceans, which themselves could help suck in CO2. For example, iron is thought to be a key limiting nutrient in the Southern Ocean. Okay, so it's the kind of marine lungs of the planet. So glaciers, the ice sheets there could be important for helping to support marine life too. And then analogues for planetary exploration. Well, I guess there we're thinking in particular about places like the icy moons of Jupiter and Saturn, places like Europa or Enceladus, where I think there are subsurface oceans under the ice. Also maybe ancient Mars, where there's evidence that there was active glaciation there too. So this is where I'm going to really just go into a few details of my first trips to glaciers, looking at that key question of what happens to organic carbon when glaciers subsume it. Yeah, so does it just stay there, or do microbes have the capability to recycle it even under those low temperatures? So, and this links into a kind of first question here: is how do you actually go and sample them? So this is kind of showing one way, directly with a chainsaw. So this was my first glacier. So I hadn't even been skiing before this, but so never even seen any type of glacier before. So this was being flown in by helicopter to a place called Engebring in Norway. It's an outlet glacier from the Svartisen ice cap. And it's unusual, Engebring, in that it allows you to get directly to the base of the glacier. The reason for that is that they've drilled a load of subglacial, of hydroelectric tunnels, right, for power purposes, right next to the glacier. And as part of that system, they also put in this extra little tunnel, a subglacial kind of lab and tunnels, which allowed you to access via a metal plate the very underside of the glacier. So this shows you a picture of the tunnels and some of the entrances to this tunnel network. So we went there for a week. So we were staying in these tunnels kind of underground, only rarely saw daylight when we went to one of these little outlet tunnels. Went up to this plate, we took it off, and then almost seems pretty primitive. You get a hose, hot water hose linked to a generator, which you then target at the base of the glacier because you're right in there. And then that will slowly start to melt away that ice. And then over time, you move that hose forward, it melts out, and so on until you melt out a nice tunnel. And all the time, I guess the glacier is moving towards you, in this case, about 1.5 meters a day. So you don't really see it move, but you kind of do a time lapse, you'll easily see it move. So you're melting it out faster than it's moving. So what we did here was melt out a nice big cavern, then we can go in with, in this case, chainsaws, electrically driven chainsaws, and start sampling that subglacial debris. So it kind of, that picture in the middle shows kind of standing on the bigger debris at the bottom, and then you're sampling the subglacial ice just above it. Then we're just storing those and shipping them back to the lab to work on. Okay, so that's not everywhere as well set up though as Engebring for accessing it through these nice tunnels that are already there. So for other places, my kind of next trip was to a place called Finsterwalderbreen in Svalbard, kind of remote part of Svalbard. So for this, you've got to do your rifle training before you go there because of all the polar bears. Get there by a converted fishing boat and then by a little Zodiac to drop us off with all our gear, and stay in a remote hut for a couple of weeks while we again try and sample this subglacial debris as best we can. So yeah, this is a view of our sort of daily travels to the glacier. So over a frozen lake, and there's a glacier in the distance there. So Marek Steele and Greg List there in front of me. When you get there, it's using pickaxes even to try and make a tunnel into the side, using chainsaws. What we also found with these pressure ridges, so you get some of the debris, that kind of third picture at the top there, where the glacier comes to the edge and starts to turn, you can get material thrust up, and you can actually get these bands of what was originally subglacial debris, which you can then find at the surface and start to sample. So that's what we're doing there as well. And so yeah, living there, had a polar bear visit one day, had to scare off as well. So it was, and saw the Northern Lights. So it was a great trip, and we ended up with some very good samples from that as well. And then from there it was on to Greenland, where I know it's a place that Karen has been as well. It's where I met Cameron for the first time as well, a place called Kangerlussuaq. So if you just drive up a track from Kangerlussuaq, you can see this within about, I don't know, half an hour or less. In the main part of the main sort of Greenland ice sheets, a different scale to the other ones. And here, again, doing the same sort of thing. This is a glacier called Russell Glacier. Go to the edge, dig tunnels, find pressure ridges on the top, try and sample this debris, bring it back to work. This first picture here on the left, you've shown this, again, this nice band of subglacial debris we've got from one of these pressure ridges that's been thrust up. What we found with this study is that, okay, big question was, what happens to the carbon, the soil, this vegetation, potentially marine organic matter that's overridden by different glaciers? So what we found was that at least some of it can be converted to methane over time, even at low temperatures. So we simply incubated them, simple cultures, and then see what happens to them. Measure the rates of methane production over time. So what we found is at different sites, methane generation seemed to be either organically driven, things like acetate are driving it, others it seemed to be hydrogen that's driving it. So different pathways for the methane generation. If you start to try and scale up through some modeling about, take those rates of methane generation, make some assumptions about how much organic matter is under glaciers and ice sheets, and how much of that organic matter is used by things like oxygen and other electron acceptors before it can be converted to methane, then you can come up with some estimates onto how important and how much methane might be generated, for example, under the thick sedimentary basins which underlie Antarctica. And so this is the key paper that was led by Gemma Wadham. And this is looking and suggesting that actually quite a lot of methane might be produced, particularly under Antarctica over glacial cycles. And that might actually go on to form substantial methane hydrates, which on potential deglaciation could create enough methane, if it's not oxidized quickly enough, to affect climate, potential climate feedbacks. So that was my kind of first introduction over the first couple of years of my forays into glaciology, where I started out knowing nothing about glaciers. I haven't even read a textbook, and then suddenly I'm sampling the things. They're actually learning as I went and learning more about them and a bit more about the subglacial microbiology. The next sort of topic, the big kind of next project I got involved with, again, led by Bristol, was looking at catchment scale carbon and nutrient fluxes. So this is where this glacier, Leverett Glacier in southwest Greenland, is key. I think Karen mentioned right at the beginning Camp Doom. So Camp Doom was a kind of colloquial name that people eventually gave to this this camp due to its, I guess, slight reminiscence of a cold Mordor from Middle Earth, perhaps. A bit, depending on your point of view and your state of mind. It was either a lovely, gorgeous, place, lots of ice to look at, or a somewhat sort of desolate spot, but it's an interesting place to work. So the idea here was that over a number of years, a camp was set up near Leverett Glacier, which allowed easy access to this portal, this water coming out. And Leverett Glacier is, I guess, a great spot to try and work out catchment scale fluxes from a whole glacier system because of a few reasons. I mean, I guess the first is the water comes out on land. So if you try and do this where the glacier goes out into a sea, you're going to find it really hard to actually sample the water because it's going to obviously mix with seawater. So having a land terminating glacier like this, that's what you need to try and do this sort of study. Also, the water only comes out in one place. You go to different glaciers and it might come out in several places. And again, you have the logistical issue of how much water's coming out where, trying to put things back together again. Are you sampling everything? But this one, it's all coming out of this single portal. That makes it easy to study. It covers a big area. So a lot of the glaciers we've been discussing, relatively small in terms of surface area, maybe a few kilometers squared, 20 kilometers squared. This one has a catchment of about 600 kilometers squared. So it's a nice step up from some smaller glacier studies into this more, not ice sheet scale itself, but moving up there. And another key thing about this is that there was already a study going on by the University of Edinburgh, and they were measuring the hydrology. So this was led by Pete Nino. In this photo here on the left is Andrew Tedstone, who's doing the hydrology measurements there. Adding dye in there and then measuring how much dye is coming through over time to try and work out the total amount of water discharge. So what we have at this site is detailed hydrology measurements, giving you the fluxes of water, the fluxes of sediment that are coming out. And that can be then coupled to the chemical measurements, which are, you go and measure how much iron, how much phosphorus, how much nitrates in the water. Yeah, you couple those together and you can come up with some sort of annual estimates of fluxes of things from the glacier. And there's been a whole suite of papers that have done exactly that. So John Hawkins in particular has been associated with a lot of these. He was Gemma's PhD student, now gone on to doing postdoctoral work. So, and what we found from this sort of catchment scale study is that, I guess, key thing is here for nutrient fluxes is that size matters. So if you're looking at small glaciers, you might only get a relatively small flux of, say, iron or phosphorus coming out of it. But when you scale up, just due to the size of it, and I guess it's due to perhaps more crushing going on, the longer residence time of nutrients under the glacier to be recycled by microbes, then you can actually get a lot more bioavailable nutrient coming out of larger catchments such as Leverett Glacier. And in fact, the fluxes are so much larger that they could even rival things such as inputs of wind-blown dust into the Southern Ocean, for example, as a source of key nutrients. So in terms of interactions with climate, this is another way that these systems can interact. Yeah, so they could be very important as a potential source of nutrients for near marine ecosystems. This study down here is kind of continuing the methane theme. So alongside these nutrient fluxes, there's also been a recent study by Guillaume here, Lamarche-Gagnon, on the fluxes of methane coming from Greenland, from this Leverett catchment as well. And the little element of this that I want to focus on is the isotopes of this methane. So I don't know how many of you here have had much experience of using stable isotopes to interpret sources of methane. This little graph here is showing a kind of classic plot in a way, showing the stable isotopes of carbon for methane on the x-axis there, and the hydrogen isotopes on the y-axis. Yeah, and it's not conclusive, but it's often used as a good signature of the source of the gas. So different sources of methane, so if they're from thermogenic, if they've been heated up and sort of produced hydrocarbons from organic matter, they'll have a particular signature. If they're microbial, they'll have another signature. And also if it's microbial, for some methanogenic archaea, has the source been either, for example, hydrogen, or has it been from something like acetate? They will in general give you different isotopic signatures. So what Guillaume found when he did these measurements was that a lot of them plotted within the kind of classic field for acetate fermentation. So what that means is that these methanogens, these archaea that we're living in the sediment under the glacier, we're probably using organics as a source of methane, but there's also seemed to be some mixture with hydrogen utilizing methanogens as well. So a sort of mix between, maybe dominantly organic, but also some methanogens which could use hydrogen as a source of their methane. If you look on a wider field, if you look to the left of this graph, you will see this point here under microbial carbonate reduction. It says SLW. That's subglacial Lake Whillans in Antarctica. Okay, so that's more clearly well within the field for traditional hydrogen utilizing methanogens. And then if you look at the isotopes of methane, which has been found in deep ice cores down into the base of the Greenland ice sheet, these ones down here, you've got the kind of grit core right on the left with these vertical bars just for the carbon isotopes. For example, they're even more in that sort of very left of the graph, which is demonstrating hydrogen as a potential source for this, this methane. And what this might suggest is, it's not proved, but it does suggest maybe this kind of concept of an inorganic switch in energy substrate under ice, where you might have initially relatively fresh organic matter. It's fermented to produce all these lovely, juicy or organic molecules like acetate. There's enough of it around that there's enough left for methanogens, which are sort of the base of the food chain in a way, and they can use that to create their methane. But as the sediment gets older, that sort of readily labile organic matter might start to dry up, and then the source becomes more to do with hydrogen. So, that's a suggestion anyway. In terms of the actual communities that have been sequenced from beneath these sediments as well, it was interesting that 3 of the 4 most common taxonomic units from these sediments was actually from hydrogen utilizing methanogens rather than acetate utilizing ones as well. So, I guess it's always dangerous to state too much simply from the presence of organisms, yeah. But it certainly does show that at least there are that mixture of organisms too, some which can use acetate and some which can probably use hydrogen. And that kind of links in a way to this current topic I'm doing at the moment of crushing things a lot. So it's like mechanochemistry, microbiology instead of with a chainsaw, with a sledgehammer. So, okay, here's a nice picture. This is somebody smashing a rock up. That you should be wearing safety glasses. I should say that if anybody trying this at home. But what happens when you crush that rock? Okay, it gets smaller, yes, but I think when you look at the details of it, it's slightly more complicated than that. I didn't get a source for this picture, but I did Wikipedia to try and find a nice image of a prehistoric flint, and this is what it came up with, yeah, on Google. See those little scratch marks there? I put this in to illustrate that things don't just get smaller when you start abrading them, smashing them up. You can get some interesting chemistry going on as well, yeah? So a flint is just made of silicon and oxygen, right? It's just, SiO2. It should be in it's equilibrium with the atmosphere. It should be inert, yeah? So if you hit it together, it shouldn't react. And yet, when you strike a flint against a flint, you can get enough energy released to create sparks, which can light fires. So there's something, that's pretty much an outrageous behavior for what should be an inert material. So what is going on there? And what's going on is to do with this subject of mechanochemistry. So when you break a crystalline mineral like flint, you're breaking those strong covalent bonds. And that's illustrated by this diagram on the right here, for illustrating what happens when you break quartz. And those little broken bonds, dangling bonds, they're known as free radicals. Yeah, they got too few or too many electrons. Can be highly reactive. In fact, when you strike a flint, they can be so reactive they react with the atmosphere. They can fix nitrogen and oxygen together to form nitrous oxides. They actually catalyze chemistry. And that's the energy that is released to produce those sparks. So just by crushing things, you can catalyze chemistry. So what happens when you add water to that? So obviously under a glacier, we're crushing things, but sometimes there's water present. And this is a subject of an ongoing standard NERC grant, which again with Bristol, with postdoc Bia. And this is the topic that we're interested in. What kind of chemistries can be catalyzed by these mechanochemical reactions? So if you add water, for example, to a silicate mineral, some of those radicals, the Si radicals there shown, react with water and ultimately go on to form hydrogen gas. Okay, so that can be a potential energy source for microbes. Other radicals, for example, these SiO ones, can in theory also go the other way to balance things out by splitting. Effectively, it's all basically to do with the splitting of water to form oxidants as well. They tend to be, at least in the form of quartz, more stable though, and you need higher temperatures to actually generate that peroxide, we think. But that is a sort of an area of active research. For now, I'm just sort of going to focus more on the hydrogen, where we know a bit more about what's going on. In terms of how much hydrogen, well, under Leverett Glacier, I did some simple calculations which said that, okay, there's probably enough hydrogen that can be generated by this process that could account for previously measured rates of methanogenesis under an adjacent glacier, down to about 10 centimeters thick under the glacier. Yeah, the actual sediments will be thicker than that, maybe meters, but it can show that it can at least be a component of the energy mix between under a glacier. The way I went about this was simply measured. You see that turbid water again coming out of the glacier there. We measured the surface area of that, and actually it averages around about something like 2.5 meters squared per gram of sediment you have surface area. So basically equivalent to like a decent sized room of surface area on each gram of sediment. It's a lot of surface area, a lot of these potential broken bonds, silica bonds, which can potentially react with water, even at temperatures as low as 0 to produce hydrogen when we did the lab experiments. So that is one, in an active glacier like this, it's one potential additional source of energy for the system. What we compared it to were these rates of hydrogen to account for methanogens, okay? Because that's really at the time all we had the measurements for under Leverett. But there are a whole range of other organisms that can use hydrogen, from aerobes to anaerobes. So various studies have found other potential hydrogen utilizers, such as Thiobacillus, Rhodopteryx, and Geobacter, for example, in this study here by Hamilton and all, under a different glacier. So what I was interested in, so I sent a little student project on this recently, last year, was, are there any ones that can use oxygen with hydrogen? Now, they're known as Knallgas bacteria, which means sort of bang gas in German, because when you have hydrogen and oxygen together, it's a potentially explosive mix, goes bang, because there's so much energy that can be involved in this. So what I did was took some of these sediments that we collected over the years, so from places like Antarctica, Norway, that Ingebreen one I showed you before, Finsterwalderbreen, Leverett, Russell next to it, and Lower Right in Antarctica, and did a survey, did a simple MPN, most sort of culture-based assay to see if we could find any Knallgas bacteria, ones that could combine hydrogen with oxygen, potentially get a lot more energy out of it. And what we found was the only place we found quite a lot of them, 10 to the 4 of these things in per gram of sediment, was in Leverett Glacier. And interestingly, this was the only one which had very low organic matter, so well below 0.1% organic carbon. And from looking around at the literature, this seems typical for Knallgas bacteria. When there's organics around, then they can typically be outcompeted by ones that use the organics for aerobic respiration. But when there's not much in terms of available organics around, then maybe that's when these Knallgas bacteria can actually start to compete. They can actually use any available hydrogen, combine it with oxygen, gain energy, and then they can actually autotrophically fix the CO2 into their biomass as well, rather than use organics to build them. So it's a sort of presents a potential niche for these Knallgas bacteria within subglacial environments. In terms of what they were, we did some sequencing, and they are related to Polyromonas species, which is one of the most commonly found species of microorganism under different glaciers and ice sheets. That shows a very blurry family tree of them. So the new one's just on the top of there, in between Polyromonas glacialis and Polyromonas criconites. So when you grow these things, what do they do? Yeah, proof that they grow, they take in oxygen and they take in hydrogen. Typically between a ratio of about 2 to 1, maybe 3 to 1, up to 4 to 1, depending on how much of the hydrogen is being used to generate energy and how much is being used to build their biomass. So in terms of niches, well, crushing isn't the only way to generate hydrogen, of course. If there's organic matter around, relict organic matter, fermentation will still produce a bit of hydrogen. Maybe that's a source for these as well. You get a bit of hydrogen melting out from air bubbles, so only ambient concentrations, but it'll be a little bit. You can also get hydrogen generated through the process of nitrogen fixation. So certain bacteria can fix nitrogen just from N2 and fix it into their cellular biomass in reduced form. As a byproduct of that, you can also produce hydrogen. So there's all these different potential sources that could support the growth of Knallgas bacteria. I'll just put this in before the talk, because I was just having a look around before this talk about where Polyromonas have been found, different species of them. And even in Lake Willands, I was looking through at this paper here. This is showing, I guess, the dominant genotypes of the phytotypes of different microorganisms in subglacial Lake Willands in Antarctica. If you look through one of those dominant ones, well, just over halfway down here is Polyramonas glacialis. And if you look at how they also looked at not only the ribosomal DNA, but the ribosomal RNA, which might give you a better idea of what's actually active within the environment. And for Polyramonas, it was actually, of all of them, the most potentially active at 5.43% of all the species there. Doesn't mean it was using hydrogen. We don't even know if that species does use hydrogen, because Polyramonas can also use a wide range of other organic, for example, organic substrates. But it does show that, that there might be quite a lot more versatility in some of these species than you might imagine. And maybe hydrogen could be part of the energy mix there as well. So again, this is going back to this idea of this potential inorganic switch. Okay, so maybe as subglacial sediments get older, more refractory, then hydrogen as a intermediate, at least in microbial ecosystems, become more important. That just leads me to the end now, which is really to try and bring things together a little bit more in terms of, okay, so let's say we go out to Antarctica, we get some samples from this new subglacial lake, Lake CECs. What would we expect to find there? Okay, so to get you in more perspective on this, at the moment, got Lake Willands and Mercer down here. This is on what's known as the Sippel Coast. These are relatively shallow subglacial lakes, relatively active. The water is recharged and flushes out of them on a sort of yearly to decadal scale. Near Lake Ellsworth over here, that's where this newly discovered subglacial lake is. It's meant to be a bit more, probably deeper. Its sediments have probably been there more isolated for a longer period of time. So I just put this little diagram in as well. This was actually from based on another subglacial lake, Lake Vostok, which many people would have heard about. So this is Russian territory, so where the Russians have done some deep ice cores. There are some contamination issues, which I go into now about they've sampled some accretion ice from the top of this lake. There has been some debate about whether they have actually been from contamination or not, the species that they found there. But I'm not going to go into that now. What I put this diagram into is to sort of illustrate to you how our subglacial lake kind of works, right? So here we have thick ice, the ice sheet flowing over. We've got some rock here at the base, rock and sediment. So where the pressure conditions are high enough, you'll start to get some subglacial melt, and the water will start to go to the low pressure point, which in this case is in this big depression. Okay, got sediment in here. Some of this might be sediment there originally before the ice sheet went over it. Some sediment will slowly accumulate from bits of sediment dust that come out of the ice itself as it melts. And as this ice moves over, it'll melt here. Water starts to trickle down. But as it goes towards the low pressure point here, then it can start to freeze again. So you might get this cycle of melt at one part of the lake, freeze at another one, forming what's known as accretion ice. If this happens without any water running out, and what can happen is basically an isolated system. And as the ice melts, it will release trapped air, which can be about 10% of the ice volume. And then as it freezes, it'll generally leave most of that air within the water again. So over time, you get more and more gas, which accumulates within the water. Eventually, it becomes super saturated enough that it can actually go to form what's known as clathrates, where you get basically a snow-like looking substance, which is a waterized cage, which contains pressurized gas. Okay, so you can get these interesting chemicals structures that form these clathrates if it's isolated enough. If, however, water is also flowing out of the rim of that lake, okay, then that can give enough flow through over time to prevent this sort of oversaturation process. It's more of becomes more of an open system. So when people were starting to drill into these things originally, there were big issues about whether, there would have been this pressurization process, these clathrates forming, which could cause safety issues during drilling. When they've done this for subglacial Lake Willands, which is shown on that one there by the US team, that seemed open enough that this process wasn't really happening. It was still oxic when they drilled into it in terms of the lake water from there, but there didn't seem to be this oversaturation going on. But this shows a kind of little comparison table of the kind of what we know about the subglacial Lake Whillans, this sort of relatively shallow subglacial lake that's been sampled, and subglacial lake CECs. So I guess key things to point out is that the depths of the ice over subglacial lake CECs is much bigger. So it's going to have higher pressures and resulting lower temperatures within that water underneath. Basal ice melt rate, so that's the kind of melt rate of ice which overlies the lake. So it could be similar, could be lower at subglacial lake CECs. The depth of the water column is only 2.2 meters deep at subglacial Lake Whillans. At subglacial lake CECs, don't know for sure, certainly greater than 10 from what I've read. It could be up to even 300 meters. So it could be a potentially much deeper system. And the key thing as well is the age of those underlying sediments. So subglacial Lake Whillans, about 10 to the 5 years, up to 100,000 or so, 120,000. Subglacial lake CECs, again, don't know until it's drilled into, but it could be over 1 million. So it could be potentially much older as well. What would we expect to find in terms of life in subglacial lake CECs? Well, from looking at Whillans, they found about 10 to the 5 cells per mil of microorganisms in the lake water. Also abundant life within the sediments. So this, as I said, was an active lake. It filled and flushed on sort of yearly to decadal timescales. You might expect it to be lower flushing rates at subglacial lake CECs, perhaps. So it was oxic at the time of sampling at Whillans, but estimated rates of total microbial respiration were thought to be able to drive that down within a few years to anoxic conditions. Maybe at lake CECs, because it's older sediment, because the organic matter there will presumably be even more refractory, maybe rates of respiration might be even lower, allowing more oxic conditions, potentially, depending, even supersaturated with respect to oxygen, if there is this process of melt, and then freezing again, which can drive up the oxygen levels within the water. In terms of the total energy available in Lake Whillans, what they found was that chemolithotrophs were really important. So particularly ones that could oxidize pyrite, iron sulfides, and ammonia. So in the lake water, these seem to dominate over the use of organic carbon as an energy substrate. So it might be that sort of these chemolithotrophs are really important. Though within the actual sediments themselves, they found that aerobic methane oxidation was really important. So, this kind of methane, which is upwelling, that seemed to be one of the most important drivers for microbial energy within the ecosystems, followed again by aerobic pyrite oxidation within the sediments. But I guess where that methane is coming from, is that coming from presumably deeper sediments? Is it from original organic matter that was deposited there? The actual source for what's driving that methane is an important question, as is in the water column. There's a lot of ammonia oxidation going on. Where's that ammonia coming from? Is that again coming from upwelling ancient organic matter within deeper sediments, or is it from another source? I mean, these are sort of, I guess, open questions at the moment into the ecology of these subglacial lakes. And in terms of what to expect in terms of growth rates, well, they estimated that the average doubling time for microbes, so how often, how quickly they can divide and grow, was really slow, about 196 days for doubling time. Yeah, so these are really kind of slow growing ecosystems. And they worked out a measure of what they called of growth efficiency, which is very low. So growth efficiency is the amount of energy that they use for respiration versus for energy versus how much they use to build themselves. Yeah, and they found that was really low. So basically, most energy seems to be going rather than for growth than simply to maintain themselves. So at subglacial lake CECs, what you might expect is, well, we might expect less organic matter availability, maybe driving less methane, perhaps, who knows, maybe less ammonia. The flux of inorganic debris, such as pyrite from dust coming in and stuff from basal melt, might be similar or lower. So overall, you might expect, perhaps slightly less biomass, perhaps, maybe slightly lower rates of growth overall. It might be a slightly more oligotrophic system than we're looking at in Lake Whillans. But until people go there and look, we won't know. An important thing that we hopefully will learn from this lake is, at the moment, our understanding of subglacial ecology under the Antarctic ice sheet is really limited to this one, these set of studies from Lake Whillans. There's another lake very close to Lake Williams, which has been drilled into Lake Mercer, which will also extend that. But having this other site much further away, potentially older sediments, will really extend our knowledge of how elements such as, for example, iron are recycled within the lake and maybe become more bioavailable potentially, and then can be pumped out into oceanic systems over time. The last little link is to JUICE, to the icy moons of Jupiter. So JUICE is it's down to Jupiter Icy Moons Explorer. It's a European Space Agency mission which has been launched in 2022, hopefully, to arrive at Jupiter quite a long time in 2029. It's a long-term venture. It's going to take about 3 years making detailed observations of not only Jupiter, but also its 3 largest moons, Ganymede, Callisto, and Europa. And on board are certain instruments which can be helpful in determining the composition, potentially even the organics which are on the ice of the surface of these moons. And so how we're hoping to link into this with the work in subglacial lake CECs is to actually directly link into a kind of existing program of testing for some of the instruments at the Open University, led by Dr. Manish Patel. So we're going to link into the imaging instruments JANUS and the spectrometer MAGIS, and basically use them as further test samples. So they're already planning on testing lots of pure materials, but we're hoping to use these subglacial lake samples from the water column, sort of analogues for kind of low biomass samples that might potentially be within the subsurface of somewhere like Europa, and actually use, what will the instruments be able to detect in actual real subglacial samples. Okay, kind of last slide is a bit of an advert really. So I've talked quite a bit about subglacial environments. So at the moment we have a PhD studentship. So for any final year undergraduates listening, MSc students, then please think about applying for this PhD. It's with myself and Karen Cameron at Glasgow on all things subglacial to do with biogeochemistry, particularly rock crushing as well. But hopefully it can also, with the timing, link in a bit into Lake CEC's work if that is ultimately given the go ahead. So please think about that. Ask me further questions by email if you've got any questions. And that's put out for I've overrun or anything. But yeah, thanks very much, and I'll leave it for there. So any questions? Thanks.
Thanks so much, John. That's brilliant, seeing so many different things throughout your career linking up together. It's really nice when you can do that. Has anyone got any questions that they want to kick us off with? Feel free to turn on your videos and your mics, or Charles is going to start us off. Go ahead, Charles.
Hi, John. Thanks a lot. It's a fantastic talk. I was just wondering about the nalgas bacteria. When they use up the oxygen, are they creating anaerobic microenvironments under the glacier? I wasn't sure, how oxic the subglacial environment is and what the nalgas bacteria will be doing to those oxygen levels. I was just wondering whether you could say something about that.
Thanks, Charles. Yeah, I'm glad you made the talk. So I guess it depends where they are. I mean, I guess if I go back to a little picture. So the reason I went looking for them, if you imagine where a glacier is crushing, it's right at the boundary between the ice bed and the rocks or the sediment underneath. And many glaciers, that will be an oxic environment. Not all, but depending on the conditions. So there certainly could be a niche there for them there. I mean, as they respire, yes, they will be using oxygen up, and I guess it will depend on the rate at which they use it up. I mean, one fascinating aspect which I've thought of as well, which I've got a student working on at the moment, is that if by crushing you can produce oxidants such as hydrogen peroxide as well as hydrogen, which in theory you should because you're splitting water, then bacteria such as Polyramonas have catalases which can convert some of that peroxide into oxygen. So in theory, even if you had no oxygen to start with, maybe they can generate their own oxygen by their catalases. So I don't know, but in terms of how important they will be in terms of driving down oxygen anyway, I think, we don't really have an idea at the moment as to their in situ rates of activity under in situ conditions. So, but that's something that we could be interesting to look into. Yeah,
great, thank you. So.
Any other questions? Joseph, go ahead, Joseph.
Hi, that was an excellent talk. I would maybe if you could go. I maybe this has been published, but I missed it because there's so much that's come out of Camp Doom there. I'm glad I now know it's called Camp Doom. This is a revelation. But have you guys done a budget on the dissolved inorganic carbon that would be coming from surface melt, and how much of the methane comes from superglacial sources, I guess both dissolved and particulate, versus subglacial sources, or I mean not just methane, but bicarbonate as well?
Thanks, Joe. I think in terms of the bicarbonate, I guess that's been calculated by generally mass balance from the other, from the deficit from counting all the other ions together in general, rather than measuring it directly, is my understanding. So there are multi-year, I think, records of bicarbonate coming from Leverett. Are they published? I'm trying to think. The person to ask actually would be probably John Hawkins. So I don't know if he's on this call at the moment, but he would be the one who would know. I don't know off the top of my head if that's actually been published in total, and if there has, as you say, been any attempt to disentangle what's come from the superglacial environment to what's been produced potentially as new bicarbonate under the ice sheet.
I think Liz might be able to go in there. Liz Bagshaw.
Hello. Yeah, great point, Joseph. It's John. It's actually on its way to your inbox soon. So yeah, I've done some budgets. I've done some modelling, and yeah, it's in progress.
Excellent to hear, because I just think it's the reason I brought it up is I just think it's relevant to this question. I mean, all these methane processes are very, very fascinating and interesting, but in terms of the whole carbon budget, how does this, what's percentage of the carbon budget are these methanogenic processes as opposed to just boring old bicarbonate? But it's I think having that bigger picture will be useful insight to it once it's available.
Yeah, no, great. Yeah, thanks, Liz, as well. Great.
Can I do another question?
Yeah, only if you tell us a little bit about Camp Doom as well. Yeah, go for a question.
I don't like to talk about Camp Doom too much. It's starting to laugh.
Very good.
But yeah, I still want to go back and do more science there. It's like a strange, like psychological hold over me. But I wanted to ask about subglacial lake CECs. I don't know if you're allowed to pronounce how you're supposed to pronounce it.
I wasn't sure. I went with the safe one. I have to admit. Yeah.
So it sits at kind of near the ice divide of like what, three ice streams?
That's my understanding. Yes.
And I just wondered, how do you think that's going to influence the fluxes of water in and out and the potential residence times of the microorganisms in there? I think it's like a really interesting glaciological site. And yeah, what are your opinions on that?
I guess my first opinion would be to call a hydrologist. But I mean, I guess because it's at that divide of three glaciers, I guess the key question, is it going to be stable because of that? Or is it, if there's, movement of that place where they all join, is that going to make it unstable, I guess, as well? So it's something I've discussed a little bit with Neil Ross at Newcastle. And yeah, in terms of stability, there certainly seems to be deep sediments, which 30 meters of sediment within the lake, and they would have accumulated relatively slowly. So maybe on a pragmatic level, that would suggest that it's at least been stable for a while. But beyond that, I would call a friend and call in some proper modelers and hydrologists, Liz, I'm afraid, to answer that.
And are they going to be able to core any of that sediment? Are they going to get some back?
Yeah, the aim is, I mean, in terms of this call, the Then there were meant to be two funded to look really at the sediments and look at the paleo records in terms of the history of the Western Antarctic ice sheet and when it was deglaciated. And then two were really to focus on the microbial ecosystem within the lake. So there were definitely, well, assuming again it goes ahead, there should be two studies which are definitely planning to get samples of the sediment and look at it in terms of the records.
Thank you.
A question from Eva, I believe.
Yeah, hi. Thanks for a really nice presentation. I just have a question about this thing you referred to as the inorganic switch. Do you think that it's really going to be just inorganics, or that there might be any kind of radical or redox reactions leading to production of organics under the ice?
Okay, well, I'm trying to. Okay, so in terms of the inorganic switch, I guess that was talking about the switch from kind of short chain organics to hydrogen, in particular to support methanogenesis, but also potentially for other ecosystems. But I guess in terms of chemo-autotrophic production, the key one seems to be aerobic pyrite oxidation. So certainly, as that, there's been studies by Eric Boyd on Robertson Glacier, which has shown that rates of chemo-autotrophic assimilation of CO2 can be very important as a pathway under glaciers, and under places like ice sheets where the organics lability should be driven down over time. I think they've become even more, personally, I think they've become even more important. Things like pyrite oxidation in particular, I think could be a good source of energy, as long as there's oxidants such as oxygen or maybe nitrate. But if the oxygen's driven down, then it's going to really reduce the energy available to the ecosystem. So I think the oxygen content is going to be a key parameter to understand and how that changes with time.
Thank you.
So we're just past the hour, so I just want to say that in 2 weeks' time, on December 17th, Casey Bryce will be talking to us. She's at the University of Bristol, and talking about oxidation and banded iron formations. There is another question if you've got time for it, John. If you can.
Yeah, go for it.
So Megan's asking, have you looked into methylotrophs and whether that can explain some of the unusual isotope values?
Okay, so yeah, methanotrophs. So methane oxidizers. So that is something which Marek Stibble, who I showed in some of those photos, he's got a project out in Greenland at the moment, I believe by Leverett again, to look at exactly this question. So what kind of methanotrophs are out there? In Guillaume's paper that I put up before, looking at the fluxes of methane, in terms of, there were definitely methanotrophs found within the sediments as well. In fact, in higher abundance than there were the methanogens, I believe, in terms of taxonomic units. So they're definitely there. In terms of their activity, again, this is from Guillaume's paper, I think the overall estimate was about maybe 17% of the methane which is coming out is being oxidized by looking at these changes in the isotopes. Well, that compares to in Antarctica, their estimates are actually 99% of the methane is being oxidized in subglacial Lake Whillans. And I guess the difference there is that that is slowly diffusing up and it's going into this more stable water body and there's time to oxidize it. While in Greenland, it's coming up and maybe it's being flushed out relatively quickly before it has a chance to oxidize. So I think there are some, and also what's doing the oxidation. So is it all oxygen or are there other electron acceptors involved, such as nitrate or iron? So I think, there's lots of active research to be done, but the kind of big scale thing is that Greenland, it seems to be more of the methane comes out unoxidized, while maybe Antarctic lakes, there's more time for the oxidation to occur before it comes out.
Thank you. Any final questions from anyone? Yeah, I think, or is that Marek going to ask a question?
No, I just wanted to, or I was thinking of responding to the methanotrophic question, because it's actually true that we seeing a lot of methanotrophs or methylotrophs in Greenland, and they are very likely to actually change the isotopic signal. So it's a simple answer is yes, there's something going on, but we're still looking into that, and it's taken ages.
How long is your project going on for, Marek? You're out again next year?
Like 1 billion years, it feels, but yeah. We've got like hundreds of vials in the freezer waiting for them to be analyzed. But that's mostly like anaerobic oxidation of methane. But like from the sequencing data, it looks like normal oxygen thanatos are like the dominance of the community, though, of the assemblage that is being exported. So maybe like that's by the margin, like short of where there's plenty of oxygen, that would be the dominant reaction probably in the system, but who knows?
John, did you want to pop a question?
Yeah, I have a quick couple of questions, but I don't want to hold anybody up. So I don't know if we're sort of segueing into the post-seminar phase here or what, but I just wanted to say really quickly though, also, it's really great to see people kind of like sharing useful, information and tips and such across the seminar. That's kind of really what part of the intention was to have these seminars, and so that's really nice to see working. But thanks, John, very much for a really interesting talk. And I've got a question that's, I guess, a sort of a legitimate question, and then I've got a dumb question. But I'll ask the dumb question first. So, why don't you get that kind of hydrogen being produced when you typically get hydrolysis types of reactions? Like we don't, oftentimes, we teach hydrolysis as being a protonation reaction, and yet you're showing a silica hydrolysis and it's producing hydrogen. Is that because of something to do with the kinetics of the rock comminution, or why doesn't it just turn into like make the solution more acidic and that's about it?
Part of them will. So part of the reactions, probably a majority, will actually, my understanding is, go on to form protons. But there's a certain proportion, and that might, I think, depend on pH as well, which go on to form hydrogen. Okay. And I think the reason for that is simply because, again, of the very high kinetic rates, perhaps, of these very unstable free radicals that are formed due to the splitting of the bonds. But so you're right, in that you will also get
level of hydrogen. Okay. In that regard, so you showed, I took a peek at your paper because it looked really interesting, the Nature Geosci paper, and you compare the results under the glacier to like groundwater. But the groundwater concentrations are in equilibrium, right? As we know, with whatever microorganisms are down there using that hydrogen. So does that suggest that whatever microbial community is involved in subglacial, that sort of ecosystem, it's not got enough time to take up the hydrogen, or why do you think the rate or the concentrations are so much higher?
The concentrations of methane, or
I thought you said I thought you said of hydrogen in those.
Right. Well, yeah. Well,
by an order of magnitude.
The concentrations of hydrogen is actually an interesting question, because I'm not aware of any published studies on the hydrogen concentration of subglacial waters, and actually that would be quite an interesting thing to know. We got methane concentrations. But if you look at studies on marine sediments or freshwater sediments, they generally, as you say, they use hydrogen as a kind of almost a proxy sometimes for what is the terminal electron acceptor in the system. So what is the process? So if you've got oxygen as the electron acceptor, you would expect that to drive hydrogen down to a very low level.
Yeah, no, I'm talking about hydrogen, not methane. Sorry, in the paper it says hydrogen concentrations under, I think, is the Greenland ice sheet, or something like 200 to 500 nanomolar.
Sorry, yeah. So that's So at the bottom of these ice cores, they've measured relatively high concentrations of hydrogen.
Okay.
And so I guess you could look at that two ways. So if there are microbes there, why haven't they used it? If it's in a
exactly.
Yes. Maybe. Well, I guess there's just an open question on that. It's something which would be, I think, interesting to do to find out what are the kind of equilibrium levels of hydrogen that you get with different subglacial microbial communities. Because at the moment, all the studies, I think, have been done at more sort of temperate temperatures, warm temperatures.
Yeah, groundwater, as you said in the paper.
So maybe at colder temperatures, there's a higher threshold. Maybe they need more hydrogen. I don't know, but it's something that would be interesting to look at as a topic, I think.
Cool, thanks.
Okay, I think we should leave it there. It's been brilliant having you on, John. Thanks so much for your time.
That's great. So thanks everybody for coming up.